So this afternoon, in the next 2 hours, we're going to do some more impossible work, which is to cover off options for nuclear power in 2 hours. And there's really three parts to this. The first part is kind of a level setting. So some folks don't know as much about nuclear power as others. And in order for us to canvass the key questions that are on people's minds, we just want to do a kind of brief, call it Nuclear 101. And we have a couple of speakers to do that. Julia Turner, Deputy Director of Nuclear Strategic Policy from Natural Resources Canada, and Arthur Situm. He's the Canada Research Chair in SMR Safety and Licensing, University of Regina. And so they're going to give us the basis for understanding these options. And then we have a panel of experts, many in the room, to answer kind of like the 5 most important questions on your mind. We're going to post those questions so you can see the ones we picked and see if they covered off those, the what's actually on your minds, and we can add to those. And then finally, we've got Zaid Keldani, who's from Ontario Power Generation, and he's just joined us as of yesterday, and he's going to speak to the SMR development that's occurring in Ontario and the work that he's also doing in Alberta. And so those speakers that were going to help do that, a load just got taken off of your back because Zaid is going to provide us with some firsthand information on what's going on with those developments. Okay, so without any further introduction, maybe Julia, I could turn it over to you and thank you, and please add anything else you'd like to add by way of introduction to yourself. Over to you, Julia.
Absolutely. Can everybody in the room hear me?
Yeah, we hear you. Thank you.
Excellent. Thank you. So happy to be here with you today, everyone. Hello, my name is Julia Turner. I'm the Deputy Director of Strategic Policy for the Nuclear Energy Division at NRCan. And I'll just walk through a few slides with you, and then I'm happy to pass it over to Dr. Situm, who I think has a wonderful presentation for you guys as well, and will answer a lot of questions. So just confirming if you guys can see my slides. There we go. So today, if you can go to the next slide, I'll chat briefly with you guys about the nuclear energy renaissance. Some of the engagement that we've been doing with Indigenous groups and communities and the things that we've been hearing with regards to nuclear energy. And finally, just a snapshot of governing nuclear industries in Canada and what it includes. But the expert panel that you'll be hearing from later, as well as some of the other speakers, are really well placed on these subjects as well. So I think you'll get a lot of great overview. The next slide, please. So just to launch us off, you might be wondering why everybody is talking so much about nuclear energy lately. I certainly see it in the news, though I work on nuclear energy, so I think about it every day. But even my friends and family are talking to me about it more and more. And it's really about 3 things. Rising electricity demand is a big one. You all probably have smartphones and are Googling and using AI daily. We're driving more and more in hybrid and electric cars, and all of that requires electricity. So that demand is increasing. Now, we could just build more coal or gas or something like that, but we know that that's bad for the environment. It's bad for greenhouse gas emissions. So that's why we're talking about nuclear energy, is to also meet our climate change goals while also addressing increasing electricity demand. Nuclear energy is stable, reliable, and it's non-emitting, meaning there's no greenhouse gases. And finally, we're talking about it because of energy security. When you turn on the light switch, you want to know that there's electricity on the other end of it, and nuclear is a stable and reliable source of that electricity. And in Canada, we have a lot of the resources that we need to produce electricity through nuclear energy. So our dependence on other countries is minimized. Next slide, please. Just want to give you guys a snapshot of what the Canadian nuclear sector looks like. So there's a number of steps in the nuclear energy supply chain, and Canada has all of them. So that starts in Saskatchewan, where there's uranium mining and milling. And then in Ontario, where there's refining, conversion, and fuel fabrication of fuel for nuclear power plants. We have nuclear power generation, which is number 6 in Ontario and New Brunswick at the commercial CANDU reactors that operate there. And looking forward, there are waste management projects that are planned in Canada. So we have 17 CANDU reactors, as I said, in Ontario and New Brunswick. They meet 14% of our electricity demands, significantly more in Ontario. I think it's about half. Over 55 years of safe commercial operations, and a significant employer of highly qualified personnel across the country. We have some refurbishment projects that are underway in Ontario, as well as some new projects that you'll hear about later, and as well as some waste management projects underway. Next slide, please. So I've mentioned it already, nuclear energy is a really important source of electricity in Canada. It's the second largest producer across Canada, despite only having reactors in Ontario and in New Brunswick. This is expected to increase as we want to meet our climate, economic, and energy security goals. And as I already mentioned, the largest drivers really are increasing electrification, decarbonization, and power for new businesses. Next slide, please. So you'll hear from a lot of these people later, but who's interested in nuclear energy in Canada? Obviously, Ontario is probably the largest and the most far along, where the bulk of our nuclear energy sector is concentrated, and they're planning to add significant new capacity from both small nuclear, which you'll learn more about, as well as large-scale reactors. We also have New Brunswick, who have an operating reactor and are looking at more. And there's a handful of other provinces who would be newcomers to nuclear energy who are also looking at it. Worth noting as well that there are some Indigenous groups who've taken a real interest in engagement on nuclear with their provincial utilities. And we're also seeing some equity partnerships in nuclear projects, including the North Shore Mi'kmaq Tribal Council investing in ARC Clean Technologies, which is an SMR vendor. Next slide, please. I wanted to quickly touch on some of the engagement that NRCan has done with Indigenous communities. As you might be aware, during the initial build out of nuclear energy in Canada, which was done mostly during the 1960s and 70s and onwards, not a lot of Indigenous engagement took place. Moving forward, we know that needs to change. So there have been some ongoing engagements by the department, including in the development of a small modular reactor roadmap in 2018 and an action plan in 2020. And there's some stats on the slide in terms of those discussions. As well, from 2020 to 2023, there was an update of Canada's policy for radioactive waste management and decommissioning. And we also took some targeted engagement last fall for policy development. And you'll see along this side of the slide what we've heard during the course of our engagements. Preoccupations around risk, safety, and the legacy of the nuclear industry, concerns about radioactive waste, potential harm to biodiversity, wildlife, and species, a concern about transportation of nuclear fuel through traditional territories, inadequate sharing of benefits, and the emphasis of the need for free, prior, informed consent, and ensuring that treaty and Aboriginal rights are respected. Next slide, please, if you will. So on this slide, this highlights some of the key participation and partnerships that are happening with Indigenous peoples within the nuclear sector. I won't get into all of them. I think Arthur will actually drill in on one of them that's a little further down on the slide. But suffice to say, there's some real interest and appetite in the sector to partner with Indigenous communities in order to move projects forward in a good way. Next slide, please. So here, I won't get deeply into regulatory process at this moment, but suffice to say, wanted to talk about the fact that in Canada, the nuclear industry is regulated by an independent arm's length regulator, and that's the Canadian Nuclear Safety Commission. The process is listed here on the slide, but the main takeaway is that nuclear projects are subject to regulation throughout their entire life cycle, from the initial project assessment right up until the very end of their life. And the CNSC only issues licenses when applicants are deemed qualified to carry on their activity and have demonstrated that they'll protect the health and safety of persons and the environment, will maintain national security, and will adhere to Canada's international obligations. Next slide, if you don't mind. Folks are likely also aware of the Impact Assessment Agency of Canada and their process for reviewing projects. So the CNSC and IAC, the commission that works on the Impact Assessment Act, work together to regulate nuclear projects in Canada through an integrated impact assessment process, and that's outlined a bit on the slide there. These processes all include Indigenous and public consultation throughout the process. And my next slide, just to wrap up, I thought I'd mention just a little bit about what the federal government does and what the provincial government do on nuclear energy before passing it over to Dr. Situm. So the federal government is responsible for regulating nuclear energy through the Canadian Nuclear Safety Commission. That's not something that's delegated to provinces. The federal regulator is responsible for all of those all of that regulation. We develop and enforce federal legislation, the Nuclear Safety and Control Act and the Nuclear Fuel Waste Act, for example. We're responsible for duty to consult in the implementation of the United Nations Declaration on the Rights of Indigenous Peoples, engagement with Indigenous nations and communities, and we're responsible for supporting R&D on nuclear energy as well as policy development. And finally, we manage Canada's international commitments to nuclear energy. Provincial governments are responsible for their electricity generation options and what they decide to deploy, and that includes whether or not they want to include nuclear energy in their energy mix. They also decide the market structure for their electricity, public-private ownership of utilities that may or may not operate nuclear power plants, and they collaborate with the federal government to ensure compliance with safety and regulatory standards. We work in partnership with provinces on innovation and R&D development initiatives, and provincial governments also engage with the public on local nuclear energy projects and decisions. So I think that's the end of my presentation. Thank you very much for your time, and happy to pass it back to the organizers.
Thanks very much, Julia. And we're going to go directly into Arthur, and then we'll get a few questions at the end. We've posted the panel questions, so I think some of those will be questions that are on people's minds. So take a look and see if they cover your interests. And we'll be answering those questions as part of the panel, which Arthur is part of. And so over to you, Arthur. Thank you.
Thank you very much. Okay, let me go ahead and share my screen here. All right. Okay. Can you, just going to hide volume controls. All right. Able to see and hear me okay?
Yes.
Just checking.
Yeah.
Okay, good. Okay,
Slides,
hello everyone. Excellent. So hello everyone, my name is Arthur Situm. I'm an assistant professor from the University of Regina, and I'm going to be going over kind of a bit of a nuclear 101 today as a primer before we get into our panel discussion. So just kind of a little background on myself. I'm at the University of Regina here, where my work generally focuses on looking at corrosion of SMR materials and fuels. My overall work here is I teach nuclear engineering and nuclear engineering licensing with a particular focus on reactor safety systems. And so this is my research group here at the bottom. Kind of broadly, the kind of work I do in my lab is working on different advanced fuels, looking at performance of components within water-cooled designed reactors, developing radioactive waste management strategies, particularly around used fuel, and then also looking at a prevention of corrosion in something called molten salt, which is sort of a kind of advanced coolant that's proposed for certain advanced designs of reactors. So I always like to start off every talk I give with kind of the basic kettle analogy I like to use here. So if you think about nuclear power, if you just sort of boil it down to its simplest sort of components, you have some kind of heat source. You're boiling water to create steam. That steam is being used to turn a turbine, which then creates electricity. If you're looking at something like a coal power plant or a natural gas power plant, it's a different fuel that you're using to heat the water. In this case, we're using uranium rather than methane or coal, but it's the same basic design here. And the one caveat I always like to add whenever I give this slide is that obviously that water coming out of the kettle is recondensed and put back into it. In this case, for the reactor, we would recondense that water and put it back within the actual reactor vessel itself. That's what you would use use of like a cooling tower or something along those lines. All right, so kind of at its basic core, when you're looking at nuclear energy, you're thinking about something slightly different from most forms of energy that we use here on Earth. Most of the time when we're thinking about energy, we're using some kind of process involving electrons. Either we're breaking chemical bonds apart, like you would for burning a fossil fuel, or maybe it's something like a photovoltaic cell where there's sort of transfer of electrons. In case of nuclear energy, we're talking in this case about breaking the nucleus apart. And there's a form of this called fusion where you could be fusing small, very light atoms together of hydrogen. This is one of the reasons why nuclear energy is zero carbon, because there's no breaking of carbon bonds producing CO2. You're breaking the actual nucleus itself. And that kinetic energy that comes from the atom splitting apart is primarily where your heat is coming from. When we're thinking about the atom itself as kind of a fundamental thing, there's really sort of two components that we care about. There's the electrons. It's not very important in the case of nuclear energy, but much more important are the number of protons and the number of neutrons. We think about the number of protons, that decides what element we're dealing with. And when we're dealing with the number of neutrons, that determines what its isotope is. So a common thing that'll come up today when I'm going through things is comparing uranium-235 with uranium-238. They're both uranium atoms, but they're different isotopes. So uranium-238 has 3 more neutrons than uranium-235, and it has very different properties for that reason, as we'll get into. So when you're thinking about breaking an atom apart, in this case, uranium-235, you're looking to add some kind of an additional neutron to that atom. It's then going to result in it splitting into 2 different constituent parts, releasing heat, 2 different fragments that we call fission fragments, and then a series of fast neutrons coming out from the actual atom, usually around 3. These fast neutrons can be then used to create additional fission reactions, and the whole reaction is then self-propagating. So you're not necessarily shoving additional fuel into it. It'll essentially sustain itself when you have when you reach what's called a critical mass. There's a caveat here, though. Those fast neutrons coming out from when you split the atom are typically going too quickly to be absorbed by other uranium atoms. And so instead of causing additional fission, usually they'll ricochet or they'll leave the actual reactor in most designs. So what you need to do is slow those neutrons down somehow. And for that, we use something called a moderator. And in this case, in Canada, we use what's called heavy water. And I'll talk about that a little bit more in a second. But light water, or regular water, can be used as well, or graphite is usually the third thing that's chosen. So when you're thinking about these fast neutrons, the process of slowing them down is kind of you can almost think of them like billiard balls, sort of bouncing off each other. They're losing energy as the ball hits additional balls. It's a scattering process. So if you think about those fast neutrons scattering through water, every time they're sort of ricocheting off a water atom, scattering off of them, they're becoming slower and slower, losing more energy. They can be then absorbed more easily by the uranium atoms, and so more likely to then cause additional splitting of atoms. This is maybe a good time to bring up sort of a fundamental thing. So we're talking about light water, like regular water. You're thinking of just H2O, so 1 oxygen atom and 2 hydrogens, which would each just be a single proton. The difference between this and heavy water is that those hydrogen atoms have additional neutrons attached to them. So they're the same chemical properties as water, and it's naturally occurring on Earth. It's not radioactive. Makes up a very, very small amount of all water that you would drink. But it's going to be a little bit heavier, and so it's less likely to steal essentially the neutrons. So it's more effective as a moderator, but it is expensive to create, and that's what we use in our reactors. So this is usually a nice sort of thing I'll go through my students with. So what if you took that water and you boiled it off? Let's say the heat increases and you're starting to turn it into steam. Sort of the effect ends up being that the neutrons then have less material to scatter off of. There's less water around. Obviously, steam is going to be much less dense than water. And so you're going to have less slow neutrons and more fast neutrons. And that ends up decreasing the overall power of the reactor. So that kind of natural feedback mechanism of the more heat you put into it, the less reactive the actual material is one of the ways in which we ensure that our reactors are safe. And this is the biggest difference when you're thinking about something like Chernobyl. In that case, you had graphite mixed with water, and the mixing of those two things in any design going forward is very, very dangerous. The Russians still operate a series of these today. They are by no means safe. And that's sort of one of the fundamental differences when you're thinking about something like Chernobyl versus any other country's reactor designs, other than the Russians. So the next thing that's kind of worth bringing up here is, remember before I said the whole light water versus heavy water aspect? Well, that heavy water will take up less of the neutrons, but it's expensive to create. But you can use light water, it's just regular water. But the difference is you need more what's called fissile material, more of the actual type of isotope that reacts, which is that uranium-235. Normally on Earth, it only makes up about 0.7% of all uranium on Earth is going to be that uranium-235, the stuff that actually splits more easily. But what you have to do if you're going to use light water, the consequence is you then have to enrich the fuel. You're essentially using centrifuges, so spinning the material very, very quickly to separate the two based on differences in weights. And then you get what's called enriched fuel or low enriched fuel. So this is when you have a somewhere below 5% uranium-235 enrichment. So in the case of Ontario and the small modular reactors they're developing, those will not use regular natural uranium. They will use low enriched uranium, and that will either come from New Mexico or France, depending on sort of what contracts Ontario Power Generation ends up utilizing. But this is something that's done in a number of different countries, usually the ones who are the Britain, France, United States, China, and Russia, for the most part. So this ends up making the biggest difference. When we're talking about CANDU reactors, it's natural uranium. Any kind of SMR design is going to use some kind of enriched uranium, oftentimes low enriched uranium. So I'll talk a little bit about the CANDU reactor a little bit, since that's sort of what all of our operating power reactors currently are CANDU reactors. This is what we might call a channel reactor. So if you see the kind of this shape of the core here on the top left-hand side, you can see a couple of workers working on it before it was installed. This is kind of one of our mid-sized reactors. Each of those channels is going to be a pressurized tube, and the fuel itself is inserted into the tubes themselves. They're these sort of CANDU fuel bundles, about the size of a fire log. So you've got a sort of a high pressure coolant of heavy water running through the tubes, and then the whole thing is essentially sitting in a tank that's around 80 degrees Celsius, and that's also going to be heavy water itself. And the presence of all this water that's around the actual fuel is one of the reasons why you have never seen a major accident associated with the CANDU reactors. There's a lot of water involved relative to the amount of fuel you've got. Something also notable about the CANDU design, before we get into sort of talking about SMRs more, we produce a lot of the world's radioisotopes. So when you're thinking about different things involving cancer therapy, a lot of that material for those cancer therapies are going to come from our reactors. We produce most of the world's cobalt-60. This is what you would use if you have like brain cancer. That's how they zap the tumor, essentially. Molybdenum-99, we've been a historical producer of it, and we're going to be making more fairly soon. For tumor imaging, lutetium-177, that's the sort of standard isotope used for treating prostate cancer, or yttrium-90 for liver or colon cancer. Things can be used for other types of cancers as well, but a lot of that, the sort of point is most of that material is coming from our reactors. In terms of what we're operating here today, would be sort of at 4 different stations. Point Lepreau, which is over in New Brunswick. It's a little 700-ish megawatt reactor. And then our 3 larger sites in Ontario that make up the bulk of our fleet, which is at Darlington, Bruce Nuclear Generating Station, and then Pickering Generating Station. There's a new design being developed by Atkins-Realis, and so we'll see if we end up deploying that as well. So kind of one of the things kind of underlying all this, I often like to touch on, which is before getting into some of the different SMR designs, it's probably useful kind of talking about what the basic economics associated with nuclear energy are. So obviously you get sort of zero carbon. If you're in a country like China, where you have a lot of coal power plants, those nuclear power plants aren't going to create smog. So that's sort of good for your citizens' lungs. Low land usage, but the basic kind of economic case behind building a reactor is fairly similar to the reason you'd build a hydroelectric dam. You have a very high upfront cost associated with building a reactor. So you've essentially put billions of dollars on the table initially to build it. And then at that point, you have a very low operating cost relative to other generation. So something like a natural gas plant. The fuel cost associated with one of these things only makes up about 17% of the overall operating costs. It's very dense. A single fuel pellet will be equivalent to about a ton of coal. And so you're not refueling them very often. And so that you're getting a lot of power out of the material you put into it. And so that's the basic kind of economic case associated with building reactors. High upfront cost, but similar to a hydroelectric dam, fairly low in terms of actually operating it for, at least on the fueling side. And the other thing that comes along with it, again, similar to a hydroelectric dam, you're looking to operate these things for a very long time. If you take care of your reactor well and you manage the chemistry well within your reactor of the coolants, you could be looking to operate it for 80 years plus at this point. We've gotten good enough with the materials we put in these things and how we operate them and understanding how any kind of corrosion takes place, that if you build a new reactor today, you're planning out for 80 years of generation from it, likely, in terms of any kind of refurbishments you need to do or likewise. So having said all that, what about small modular reactors? How do those fit into the picture? SMRs, or small modular reactors, are a little bit of it kind of turns things on its head a little bit. You have a much lower upfront financing cost associated with building it. You have less initial capital that you have to put down to actually get the unit running. So this can be good if you're fairly strained in terms of budget. Generally, on a per megawatt basis, they're not going to be as efficient as a large reactor, as just basically as a rule of thumb. But you do get to save some on that initial financing before you start to generate power. They may also be easier to modularize and faster to build. Canada is currently working on the first SMR in the Western world, and so that's really something that we'll be proving out one way or the other at the OPG site. But that is a prospect. And the other big thing associated with them is that you can put them on isolated grids. So here in my province of Saskatchewan, we have a very isolated grid compared to a lot of others in North America. There's not a lot of interties, fairly small generation units, and so it's sort of right sized in the case of a 300 megawatt electric unit for the size of our actual grid. The other thing that's kind of notable about some of these SMR designs is a lot of the safety improvements made with them. So in the case of the one that's being built right now in Ontario at the Ontario Power Generation site, it's something called a small modular reactor boiling water reactor. It's what the BWR stands for in the name. And the whole reactor essentially runs under natural circulation. So it's a very, very high reactor vessel. But what that allows is for water to naturally pass through the core itself, so you don't need main coolant pumps. And its main safety systems are also all generated by natural circulation. So the reactor itself is actually fairly short, but it goes quite deep underground. But the main safety systems are all sitting above on sort of at ground level. And so for any reason you need to shut off, keep the reactor cooled for a long period of time, you essentially shut off a series of valves called these isolation valves. And then you're opening up what are called these condensate return valves that are essentially sitting on heat exchangers, sitting in tanks of water. And then natural circulation then allows for the coolant, the steam coming from the reactor, to then be cooled naturally up to around 7 days, at which time you can top these pools up with something along the lines of like a fire truck. So that kind of passive cooling mechanism where you don't need massive diesel backup generators to keep the reactor cool is something that essentially all of our reactors going forward will incorporate as a design element. I'm talking about the project a little bit more. It's very important to First Nations engagement. Case of Ontario Power Generation, the rights holders in the area are going to be the Michi Saugeen Anishinaabe nations. There's sort of 4 of them I have listed here on the map, and you can see their position relative to where the Darlington SMR plant is going to be built. They're also very close to Cameco's fuel conversion and fuel fabrication facility here in Port Hope. And they were engaged heavily in the lead up to the actual licensing application. And OPG, I'm not involved in the specifics of the negotiations, but during the negotiations, they reached the point where they had resolved all major differences and made a joint submission to the regulator, which is the Canadian Nuclear Safety Commission, saying that any kind of remaining differences we will work out directly between Ontario Power Generation and the First Nations themselves. This is sort of sets a gold standard going forward for the nuclear industry, where being able to reach the point through consultation negotiation where any remaining differences can be worked out directly between the parties is something that should be done going forward. It's also worth noting that following the success of that, Ontario Power Generation declared where it wants its next nuclear plant to be, which is here at the Wesleyville site, which was a never built oil-fired power plant site. Again, also with the same 4 rights-holding nations involved in consultation. I'm sure the Ontario Power Generation representative can talk a little bit more about that himself. So next, I want to move on to sort of a bit of a different topic. It's that around advanced reactors. So up until this point, I've just been talking about reactors that are cooled with water. But there are reasons why you may want to use something other than water. The big thing is that you may want more heat out of your reactor. If you can reach higher heat values, there's certain things that could be useful for. But before I get into some examples, the kind of caveat I always give is that if you're going to use something other than water, you need to have a good reason for it. Water is something that humanity is very, very familiar with. Managing water chemistry and water corrosion is something we're very, very familiar with. If you move beyond water, there needs to be a good economic case for it. So some examples of that, which would be good examples, would be, let's say in the case of China, they've got a large an SMR that they're using. They're going to be using for heating their major petrochemical facility for their major refineries. It's a one that uses a high temperature helium gas rather than water in that case. Next, you'd have Bill Gates's design. It just passed its safety licensing down in the United States, and that uses molten salt as a thermal energy storage. So you're looking to sort of better balance with renewable energy in that case, using molten salt. And then in the case of the Russians, they operate a fleet of metal-cooled reactors. So this is using molten sodium metal itself. And for that, they're often using them for better reprocessing of fuel. So those are kind of good examples for why you might want to do something like this. So speaking about that used fuel a little bit, what happens with it when we're pulling it out of the reactor itself? The first step that will be involved when the fuel comes out of the reactor is it spends about 7 to 10 years in some kind of spent fuel pool. So this is a colleague of mine you see standing up on the bridge, and you can see our rods of can-do fuel sitting in this pool, this kind of giant sort of Olympic-sized swimming pool beneath him. And those will be left in there for any heat to disperse from the actual fuel itself. Water is obviously very, very good for that, and it also acts as shielding as well. Next, after that point, the standard practice across the industry is to put it into some kind of cask, temporary storage container of some kind. You can see the example of the main one we use here in Canada that's used over by Ontario Power Generation again. It's got sort of these slots built within it that the actual bundles themselves will kind of be slotted within, and the whole thing is kept under an inert atmosphere. The containers are obviously very heavily shielded. It's been a while, since about 10 years since it comes out of the reactor, so it's not nearly as hot as it was once it came out. And so it's sort of warm to the touch, but there's sort of very little sort of radiation you're getting actually coming through the concrete itself. And so at this point, this is where it would stay until you do something else with it, which I'll talk about in a sec. This is also maybe a good sort of time to bring up a caveat. So the amount of radiation you're talking about when you're living next to one of these plants is very, very small. Everything is heavily, heavily shielded. So if you're living next to our largest nuclear power plant, which is the one at Bruce Nuclear, I won't go into sort of what the units mean. I'll just kind of go kind of them relatively, but you're getting essentially an additional background dose of 16 microsieverts per year. Sieverts is just a unit we use for dosage. But to kind of make that in comparison, if you take a sort of a cross-Canada flight, you'd be looking to, during that flight time itself, you're accruing around 20 microsieverts worth of dosage during that time. So it's about the equivalent of taking a flight to go see family on the other side of Canada. And then your overall background dosage you get just from either radon gas or exposure to UV radiation during the year is going to be around 1,800 microsieverts. That kind of sort of puts things in comparison. So what about that fuel management? How does that look like in Canada? What are other countries doing? What's going on there? So this is what the actual image looks like of the used fuel storage facility over at Bruce. So you can see each of the casks lined up. Each of them are numbered. You add an additional one when you're taking fuel from the actual pool itself. Kind of putting that in perspective, size-wise, this is sort of our oldest power plant at Pickering. And you can see the actual used fuel storage building here. It's kind of size relative to the actual reactors. So it's not small, but it's not massive either. You're talking this used fuel is a fairly small amount of volume. And so you're keeping it essentially within a large building, where the actual building itself, essentially you obviously want to keep it guarded, but it's not really doing anything while it's in there. Now, what do you do after that? That's one thing to say it's sitting in sort of some kind of storage building, but what would kind of be the next steps? Because eventually you'll want to do something with it. There's kind of three general sort of philosophies that different countries take on when they're thinking about fused fuel management. The first one is maybe you might call extended stewardship. So extended stewardship would be sort of the approach the Dutch are taking over in the Netherlands, where you essentially have some kind of interim storage site and you're looking to extend operation of it for over 100 years. At this point, essentially, you're saying, well, we might want to use the material in the future, maybe for some kind of other advanced reactor type or something. Or maybe there will be better ways of reprocessing it in the future. So it's sort of extended stewardship of it is the approach. This facility is actually kind of weird. The whole inside of it is partially a museum. It's very, very bizarre, but interesting. The kind of next approach would be what I might call kind of the French approach, where sort of a national priority is to minimize the amount of waste you have, period. And so to do that, you have to go through something called fuel reprocessing. This would be their large fuel reprocessing plant right here called La Hague. This is not cheap. It's not easy either. They do this for a lot of different European countries as a service. But that is another approach that can be taken where essentially you're taking the fuel, reprocessing it to remove any kind of long-lived products like the remaining uranium or plutonium from the fuel. And then you're left with a very small amount that would actually be waste itself. And the rest of it is then cycled back into your reactors as additional fuel. It's not cheap, but it is another option. And the last one is what you might call using some kind of storage within what's a deep geological repository. So an example here is sort of the leader in the world doing this is Finland. We're already building their used fuel repository. And the idea here is to essentially put the fuel so far beneath the earth. Essentially, you took it from the earth as when you mined it, and you're placing it back in as its final resting place. And so the approach here is to place it within some kind of corrosion-resistant container, deep underground, surrounded by clay materials that can sort of stop anything if it were to ever the container would ever be breached, so far away from humans or nature that you wouldn't have any kind of effect for it for a millennia plus. That's the basic idea behind the approach that Canada's decided to take. And the underlying rationale there is, while the first two approaches could have their merits, they essentially leave the burden on future generations to figure out what to do next. The third approach essentially proactively deals with the problem, saying we will place it in a way where it's safely disposed of so it isn't left to our children's children to figure out what then to do next. And the movement of fuel, in this case, to a deep geological repository, would happen via again another cask like material, like container design, where the fuel is then inserted and brought across the roadway, and that's usually heavily. It's not concrete, rather it's heavy reinforced steel that the fuel then sits within. It's sort of a mock-up of what one of those containers looks like when you're driving this down the road. Next thing I wanted to sort of bring up is kind of what this design looks like. In the case of Canada, I'll just kind of go over this briefly, but I'm happy to answer questions about it. The fuel bundles themselves are sitting within that container itself, which is coated with copper. Copper is very nice. We see it kind of naturally. You can naturally find samples of copper on Earth. That's why most prehistoric tools that were metal were made out of copper metal. It's very corrosion resistant. That then goes within a clay buffer box of a kind, and then placed within the actual repository itself in very stable granite within the Canadian Shield. And the important thing to bring up here in this case is that, similar to any kind of reactor site, these waste sites have to receive free, prior, and informed consent as well. In the case of this deep geological repository site in Ignace, Ontario, there's a referendum held both by in the actual town of Ignace where it would sit, as well as Wabigoon Lake, Ojibwe Nation, who are the rights holders for the area, and both have to consent to the location of the actual waste site before it can be constructed, and that's something that's been upheld by the courts in Canada as well. Okay, so I kind of rounding things out. There's sort of a lot I've left maybe on the cutting room floor here, but I want to talk a little bit about microreactors. So far we've been talking about large ones like our CANDU reactors, kind of medium-sized ones like those SMRs. There is an ability to do things on a micro scale. It gets very tricky when you go very small. This is one of those things where there's been a lot of different designs that have been proposed, At this point, most of those designs are still in the conceptual phase. But I'll show you an example of one that we did build in Canada for a time and operated for a little while to kind of give you a sense of what this kind of looks like. So what I'm showing you here is what we call the Slowpoke 3. It was a little microreactor we ran in Whiteshell National Labs over in Manitoba. It ran for around a year, kind of at the tail end of the labs. If you're familiar with sort of Canada's economic situation in the 90s, we were very tight on money, and so it was something that we decided to then close. But the basic idea behind it is that it was sort of a little core sitting in a sort of a two-story tank of water, and it would produce just enough heat to actually heat the labs itself. And it could conceivably be a little power conversion cycle put on it to create electricity as well, but that would have taken more engineering than we had money to throw at the problem at the time. As you can see, the two workers there making an adjustment to it when they were setting things up. And the whole thing was really geared towards remote communities for heat generation and possibly power generation. The caveat I want to bring up is that this is not something that Canada's really had a lot of work done on in about 35 years. So it's something that we're working towards, but there's no commercial product currently available to do this kind of thing. It's something that we'd have to put a lot more engineering into before it would be something that would be commercially available. And at that, I'm happy to turn it over for any questions.
Okay. So rather than taking questions right now, I'm going to get the panel up here and online. And then we've got a bunch of questions that are on that Arthur has partially answered. So I'm going to reinforce some of those questions, and we're going to go through those questions, get the other panelists to respond, and field any other questions, okay?